All right, everyone. This is our final push through the really difficult content in the options, section L. Once we get out of here, differential equations is much simpler, comparatively speaking. Um, I'm going to go through this not following the order of the textbook exactly. It's not the way that my brain wants to process the information. So there will be 2 or maybe 3 videos for this section. I haven't really planned that far out yet, but they're not necessarily going L.1, L.2, L.3, L.4 in that order. That being said, I'll try to reference the sections that I'm pulling from as we go through. So before we begin, I just want to remind you from the previous section about power series. Section L is all about Taylor and Maclaurin, which are special types of power series. A Maclaurin is a special type of Taylor, and a Taylor is a special type of power, which means that everything we know about power series still applies here. Okay? They still have an interval of convergence with a center and a radius, and we'll be answering a lot of questions about those. Here's what makes them different. So our general form of a power series looked like this, where A was the center, and C sub n was just some extra pieces. And really, when C sub n was just 1, we had a geometric series. So that was kind of what made the geometric series so special and kind of why it's so easy, why we introduced it, in year 1 of this course. What makes Taylor series special is how we define this C sub n. We're going to do calculus. Whoa. So our C sub n for a Taylor series is the nth derivative of the function that we're approximating with the Taylor series. We'll talk about that in a second. But it's the nth derivative evaluated at the center, at A, all divided by n factorial. Now, I have this written down twice because the version on the left matches our general form of a power series, but the version on the right is how we're going to see it in the formula book. It's where the n factorial is below the x minus a to the n, and then we have the derivative out to the right. Here is exactly how it appears in your formula book. So it's the first term is f of a. That's the 0th derivative of the function, right? The 0th derivative is just not taking a derivative at all. And since our series starts at 0, we need to put 0 in here for n. And then we multiply by x minus a times f prime of a, x minus a squared over 2 factorial times f double prime of a, etc. Of course, you could imagine having a 1 factorial and even a 0 factorial here, but we generally don't write them, and your formula book does not write them either. What makes the Maclaurin series special is what the center is. In a Maclaurin series, the center is 0. So again, this part over here is in your formula book. It's f of 0 plus x times f prime of 0 plus x squared over 2 factorial times x double prime of 0. And in fact, here are the other relevant formulas for today's video from the formula book. So you are given 5 Maclaurin series for special functions. Let's just look at, I think the simplest one of them is e to the power of x, and let's just see how that makes sense using the definition for Maclaurin series. So if our function is e to the x, what is f of 0? F of 0 is just e to the power of 0, which is 1. What's the derivative of e to the x? Oh, the derivative of e to the x is just e to the x. So that's convenient because now our first and second and so on derivatives are all just going to be e to the power of x. So our second term is x times f prime of 0. That's just x times 1. Our next term is x squared over 2 factorial times e to the 0 again, and so on. So that's how we could build this Maclaurin series for e to the x. If we tried another one, say ln of 1 plus x, I could start off by writing down a few derivatives of that. You can check my work if you want. And then we just build the Maclaurin series using the rules. So we start with f of 0. F of 0 puts a 0 in right here, and that gets us ln of 1. And ln of 1 actually is 0. So really there's a hidden first term here of 0. Whatever, we don't need to write that down. Next, we do x times f prime of 0. So we put a 0 in right here, and then we just get 1 out. So it's just 1 times x, and that is indeed our next term. Then we're going to do x squared over 2 factorial times f double prime of 0. When I put 0 in right here, we get negative 1, so that's why I've got a negative here. And the remaining part is x squared over 2 factorial. They've just written it as a 2 instead of a 2 factorial. We'll see why in a moment. For the next term, it's going to be, following this pattern here, it'll be x cubed over 3 factorial times f double prime of 0. Notice here it's not a 3 factorial, it's just 3. That didn't make a difference with 2, since 2 factorial is equal to 2. 3 factorial is not equal to 3. The reason that it's changed is because our third derivative has a 2 in the numerator, which will cancel out with the 2 from the 3 factorial, leaving us with exactly that term, and this pattern continues indefinitely. You'll see with some of them, like with sine and cosine, you get a lot of hidden terms, like that 0 at the beginning of ln of 1 plus x. Sine skips over the even powers of x, whereas cosine skips over the odd powers of x. We always have an option to fall back on the definition of a Maclaurin series as we saw on the previous page, and that's to build it this way. And that's how I'm going to start off this one. We're going to do it the old-fashioned way. So I know what f of x is equal to. So I can calculate f of 0. That's my first term, is 0. I then calculate the derivative of this function. Boom. And then I calculate f prime of 0. That also happens to be 0 in this case. Then I differentiate this function. F double prime of 0. All right, that's 2. I differentiate that. F triple prime of 0. It happens to be 6. And I could keep going until I've got however many terms I want. And we'll talk about how many terms we need later on. For now, we'll just look at these first couple. And then I write them out in a series. Remember that it's going to be f of 0 plus x times f prime of 0 plus x squared over 2 factorial times f double prime of 0 plus x cubed over 3 factorial times f triple prime of 0, etc. So the first few terms just look like this, right? The first few are zeros. This 2 is going to cancel out with the fact that this was divided by 2 factorial. The 6 is canceled out with the fact that's divided by 3 factorial. But this is really tedious. And if I stop here, you might think that the next term is x to the 4th. It's actually not. So here's an easier way in this case to evaluate this function as a Maclaurin series. Since I know the Maclaurin series of e to the x, because that's in my formula book, I can use that here. And we just need to multiply this infinite series by x squared. And when we distribute that x squared in, I see, obviously I won't see the first two 0 terms, but the next two terms match exactly what I had here, and then it ends up being x to the 4th over 2 factorial plus x to the 5th over 3 factorial, and so on. We should also get into the habit of being able to write an infinite series in sigma form. If you haven't practiced that skill a lot, give it a go here. Make sure that you could get from here to here. I don't think this one's really that hard. Okay, let's look at another one. So this one is for e to the negative x squared. We could do this the quote-unquote hard way by taking derivatives, but I'm not even going to bother with that this time. I'm going to use the easy way. I'm going to use my expansion for e to the x, and I'm just going to use substitution in this case. So instead of x, I have negative x squared. I'm just going to put in negative x squared for each of these x's, and I'll be good to go. Boom. There you go. There's your Maclaurin series for e to the negative x squared. Easy, right? Let's do another one. So now those first two, I just threw a plus dot 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 at the end. Oftentimes you're asked to show a specific number of terms. There's two ways that this could be asked. One way is for it to say, compute the first 3 or however many non-zero terms, because oftentimes there are 0 terms and we don't want to include them in our answers. So that this gives it away. I just need to keep calculating out terms here until I get 3 that aren't 0. Now here's a case where using there is no easy way. I really have to do it by calculating derivatives. You can. The problem with doing it a clever way with substitution is that we can substitute in sine of x into cosine, because we have an expression for cosine here. And we could think of that as 1 minus sine squared of x over 2 plus sine to the fourth of x over 24. But that's not a polynomial, right? We need to get a polynomial expression here. So what we actually end up having to do is substituting in this infinite series into this infinite series. So we get 1 minus all of this stuff divided by 2 plus all of this stuff to the power of 4 divided by 24 and so on. And I don't know. For me, that's just more messy than I want to deal with. So I'm happy to just start taking some derivatives. Okay, so the original function's there. I evaluated at 0. I get 1. Cool. F prime, okay. That's a derivative. Doesn't look too bad. Oh, f prime of 0 is 0. Great. We're using chain rule all over the place in this problem. Next step is going to have to use the chain rule and the product rule. Oh my gosh, this derivative's getting out of hand now. I've got -1. Great. I'll be honest with you. I didn't feel like doing the next few, but I assure you, if you bother getting down to the fourth derivative for this function, the fourth derivative of 0 is equal to 5. And this is all we need, is these three numbers. We put them into our Maclaurin series format, and there we go. Those are our first three non-zero terms for this function. So, okay, so that's one way that they can specify how many terms they want, and they can just tell you how many terms there are. The other way is by using the phrase degree. So finding the fifth degree Maclaurin expansion of this just means keep doing it until you get up to the x to the fifth term, the fifth derivative term. So it doesn't matter how many terms are skipped over before that. So you may have up to 6 terms in this case, right? Because you have the f of 0 is your first one all the way up to the fifth derivative one. Or it might be only one term if the first 5 terms are all 0. Who knows? So we can do this one the long way by taking a bunch of derivatives, but I don't want to. I want to be clever again. I've got an expansion for e to the x on my formula book. I also have an expansion for cosine of x in my formula book. So what I would prefer to do is just multiply those two together. Now, when I do this, I choose the right amount of terms, meaning for my expansion of e to the x, I don't need to include x to the sixth over 720 because I only want to get up to x to the power of 5. So having an x to the sixth term here is useless. It's likewise with the cosine. X to the sixth does not help me. And then I just start multiplying. And I didn't really show the work here because it's just tedious algebra, but I multiply the 1 by everything. I multiply the x by everything. And then as I'm doing this, I'm collecting all of my like terms. And again, I'm only bothering to do up to the power of x to the fifth. So when I distribute my x squared over 2, I'm going to do it to the first 2. I'm not going to bother multiplying it by x to the fourth over 24 because that's too large. And in the end, we'll have that right there. So we ended up with 5 terms in the answer. Notice that there are no x squared terms here. So look, that's the core of what I wanted to discuss in this video. In the next one, I'll look at more operations on Taylor and Maclaurin series. We'll talk about adding them together. More examples of multiplying them and what can possibly go wrong there. We'll do some more about differentiating and integrating them. All this is really, again, like same rules apply as what we saw in power series. And then I'll do a separate video on error for Taylor and Maclaurin, which is the final error we need to worry about in the option calc. And this one at least has something in the formula book, so that makes it a little bit easier. But to close off, though, I want to show you something really exciting. This is a moment you have been waiting for a really long time. I know. So here are 3 Maclaurin expansions that we have on our formula book. And you might notice that there seems to be some relationship maybe between the sine and the cosine and the e, right? If we were to add up cosine plus sine, and if I alternated the terms, I would get something that's very similar to the expansion for e to the power of x. The difference, of course, is with these minus signs, which It's not an alternating series, but every other term alternates. Now, think for a moment. Can you think of a number which, when raised to powers, it alternates in sign by twos in this sense? So in other words, like -1 to the power of n, that alternates its sign every other term. I want a number which, when raised to the n, alternates its sign every two terms. If you're having difficulty, here's a hint. It's not a real number. I alternates every two terms, right? Because we've got I, and then I squared is actually -1, and then I cubed is -I, and then I to the fourth becomes +1, and then it alternates from there. So we've got plus, minus, minus, plus, if we allow I to have a positive sign. So what does that mean? Well, it means that we could get that expansion out by putting an I in to our e function expansion. Okay, if we were to do e to the ix and expand that, just like before when we substituted into the e to the x Taylor series for e to the -x squared, we're just going to put ix in this time. So we've got 1 plus ix squared over 2 plus ix cubed over 3 factorial and so on. And then this I squared here gives us a -1 here. This I cubed gives us a -I, and so on. This I to the fourth just gives us a +1. Great. Well, what does that mean now? So notice over here, I've got i's only left over on every other term. Which terms have i's next to them? Well, remember before when we were alternating to put the series together, we started off with cosine, and then the second term was sine. So only the sine terms here have the I next to it. And if you don't have goosebumps right now, that means you've either seen this before or you have no clue what's happening, because we just proved Euler's identity. E to the I theta is equal to cosine theta plus I sine theta. That's amazing, and that's where we're going to end this video.